I'm going to do a quick example that just shows you a little bit of mathematics of electromagnetic radiation. This is an example that you probably could have done last year in Physics 20 if you knew the speed of EMR. It relies on two equations, V equals d over t, which clearly you learned last year in Physics 20, and the second equation, the wave equation, V is equal to F times lambda, which may be a little less familiar with you, but you've done it last year as well. It says the distance of Calgary to Regina is 800 kilometers, which we know we're going to want to convert that to meters. How long does it take the light to travel from Calgary to Regina? And should be a question mark there. And if the wavelength is 600 nanometers, what's the frequency? Nanometers, by the way, that's 10 to the minus 9. If you don't know that, that's okay. I probably wouldn't have known it in your spot either. Just look in your data sheet. It tells you that an N is 10 to the minus 9.
So lambda is meters?
Lambda is in meters, yeah, yeah. Everything that we do, almost everything that we do with lengths and distances are going to be meters, right? That's the standard unit. And if in doubt, always convert to those standard units. All right, so what do we got here? Well, we want to find, first of all, the time that it takes the light to travel from Calgary to Regina. Would we expect to be a big time or a little time? Little, small time, yeah? Like how small, like 4 seconds? Under 1 second? Yeah, probably quite a bit under 1 second, right? We know that light will make 25 return trips across Canada in 1 second. So we would expect this to be a pretty small amount of time, right? Let's rearrange this to solve for time. The t goes up, the v goes down. T becomes d over v. The distance here is 800,000 meters. The velocity here, the speed here, is 3.0 times 10 to the 8 meters per second. Now, in all likelihood, we're talking about visible light here, but not necessarily. Okay? Light can be any kind of EMR. It doesn't really matter. The speed of any type of EMR in a vacuum or in air is 3 times 10 to the 8 meters per second. We do the math here. 800,000 divided by 3 times 10 to the 8 gives us 0.00266. Repeating. So we're going to say 2.67 times 10 to the negative 3 seconds. That's a pretty small time. Joshua said it was going to be less than a second. Yeah, it's like 2/1000ths of a second it takes the light to go from Calgary to Regina. Sorry, say it again. Right here? Yeah, that's 3 times 10 to the 8 meters per second. And it gives us a time of 2.67 times 10 to the minus 3 seconds. Now we want to find the frequency. We're going to say V is equal to F times lambda. Rearrange this to solve for F. This is the wave equation that we learned last year and looked at yesterday as well. F is equal to V over lambda. The speed is, once again, 3 times 10 to the 8 meters per second. Doesn't matter what kind of EMR it is. And the wavelength here is 600 nanometers. Don't try to move the decimal place over here. Just make it 600 times 10 to the minus 9 meters. When we do that, we get 5 times 10 to the 14, 5.00 times 10 to the 14 hertz. Now, you're not asking this question what type of EMR this is, but you could figure it out now. Without looking at the table, hopefully, without looking at the table, what kind of EMR would that be? 5 times 10 to the 14. What is it? Yeah, it's visible light. Good. Visible light was 4 to 7.5 times 10 to the 14. Now, you were given a wavelength. From that, we found the frequency. And from that, we compared that with the frequencies that we memorized. And we realized that it's going to be visible light. We probably expected visible light here, but it could have been something else. All right, some homework for tonight. We're not going to work on this right now, but homework for tonight, you may have a chance towards the end of class, is to work on worksheet number 15. There are 5 questions on the worksheet. I only want you to do 1 to 4. Please do not do number 5. There's an issue with that one. So worksheet number 15, questions 1 to 4.